We have homework number 22. Wow, time is flying. And so we have this dynamics test rig. We have this double pulley. So you can see there's a inside and outside pulley to it. The whole thing weighs 65 pounds and has a radius of gyration of 1.2 feet. And the outside radius of this thing, so that's RO, is 1.5 feet. Inside is 0.8 feet. Cylinder A is 15 pounds and block B is 55 pounds. And it's attached to cords that are wrapped around the pulleys. The coefficient of kinetic friction between block B and this 30-degree surface is 25 or 0.25, and block A is moving at 6.5 feet per second downward in the position shown, which is that the height above the surface is 10 feet. And then there's this force being applied here of 110 pounds. And we want to find the velocity of A just as it strikes the ground. And we want to find the total distance that B moves up the slope before it pauses, all right? So you got to kind of think about like what's taking place here. One thing is that the external force is needed on here. You'll note that this is only 15 pounds compared to this thing being 65 pounds. Probably without that force, B might be sliding down, right? But this force hopefully is enough to make this thing go down, and then it's going to strike the ground. And now this cable is going to go slack, but B has momentum, right? And so B has momentum and will pull up. But here's another thing. C has momentum as well. So C could contribute right up into the point where its kinetic energy is going to stop, and then B is going to have a speed and it's going to keep on moving, I think. So this is sort of an interesting type of problem. There's lots of things taking place. So you have to really kind of think your way through. And I'm starting to kind of second guess some of my previously held notions about it. So let's just try to move through it and try to think our way. So here is the write-up onto the thing, and I'm going to get a few things out of the way. Let's see. I want to move a couple things over on my other screen here, and it's causing problems. Cut out. Go right there. Yeah, that's what I want. All right, so let me get some preliminaries. Move this. Let me make this smaller. There you go. Some preliminary stuff. Let me get the moment of inertias, or the moment of inertia for the main guy here. That's this. This is the thing that has the moment of inertia, and it gave us a radius of gyration. So that's just going to be mass of C times the radius of gyration squared, and the mass of it is going to be 65 divided by 32.2, right? We want to get it into slugs. And everything was given as feet, so we don't have to convert inches into feet, but here's the radius of gyration was 1.2. So putting those together, I'm going to double check my numbers. I transformed this problem. I modified this problem and did it in Excel, so I can take a look and compare. If I'm not 100% sure that my Excel is correct either. 2.9067, excuse me, 7. And these are slug feet squared. And okay, so some kinematics are going to take place. So first off, this guy is actually moving with an initial velocity going downwards of 6.5 feet per second. We need to see the relationships between this rotation here and that motion and the rotation here and this motion, right? So we can have like kind of link together all of the velocities. So I will write down what I'm doing. And so for the kinematics, omega c is going to be equal to the velocity of A divided by RO, right? You could easily just say that omega c times RO was going to be the tangential velocity here, so that's why we're saying this backwards. So in the initial one, omega c1 is going to be VA1 over RO, and so 6.5 divided by RO is 1 with 1.5, so 6.5 and 1.5 divided, we get 4.33333. And these are radians per second. Now we might want to also stick this in later on into the kinetic energy of another state. We're also going to say then that I'm looking over here at this thing here and say that VB is going to be equal to omega CRI, right? So VB1 is going to be omega C1 4.333 times my RI, which is 0.8. So that's 3.467 feet per second. Okay, so we also have this distance. This thing has moved right here. And we could find that distance this thing is going to travel up the slope right here by way of a ratio of these, right? We could write this out in a couple different ways. You could think your way through this. We know that for every revolution here, we move delta theta times R1 this direction, and then this one moves delta theta R0. So we could say that the delta S from 1 to 2, is that how I wrote it? Yeah, delta SB, right, so it's B that's moving up here, and it's going from 1 to 2, is going to be equal to so it's going up more, so the ratio is going to be inside ratio to outside ratio, if you weren't sure about that. So that's I think that's true, and that's going to be times H, right? Yes. So if you weren't sure about how to do this one, I might start to say that you're going to go yeah, so I'm trying to think how I might say this. You could say that delta theta was going to be equal to H divided by RO. Delta theta was also going to be equal to delta SB over RI. You'd set delta theta equal to each other and then solve for SB. And so that's why RI is going to show up on the top. Yep, got it right. So this is going to be RI is 0.8 and RO is 1.5. And H, we're told, is 10. So we get 0.8 times 1.5, or divided by 1.5 times 10, we get 5.33333. And these are feet. So that's how much it goes up the slope. Anything else I want to get? Yeah, maybe I want to get the height change of this after it this thing moves down H, right? So we would say delta y b1 to 2 is going to be delta s b1 to 2 times the sine, right? Because if it's going up a certain level, that's the hypotenuse, but we want the height. So we'll take the sine of theta, 5.333, sine of 30 degrees, and 2.667 feet. All right. So we're almost ready for our work here, but let me kind of like write out. I think it'd really help to have a diagram as part of this, but I almost want to kind of draw it up here, right? So let me draw this grossly exaggerated here. And I'm going to increase that up there, right? So this is state 1, and this is state 2, and dot, 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 dot. Here's state 1, and here's state 2. But at state 2, that has gone slack, right? So let me go through the things that we need to go through. You know, something I didn't do here is I didn't get the friction force, and I kind of need the friction force. So let me do this FBD, IBD little diagram here. And we've done this one a bunch of times, and we don't necessarily have to do the IBD, but I want to remind you to consider it, right? And we're going to have an X prime here and a Y prime there. And we're going to have a weight. And we're going to have a normal force. And we're going to have a friction force, and it's opposing this. F, BN, I guess. F, BF. Yeah, I guess I got that in there. And there's tension, Ft. And here's the weight of B. And there's the angle that's in there. And then this is the acceleration. So we go MB, AB, right there, right? And these are equal. So I made it kind of small. Sum of the forces in the Y prime, mass times acceleration in the Y prime. Not accelerating in the Y prime direction. So all we have is a negative WB times the cosine of theta plus FBN equals 0. FBN is equal to our 55 times cosine of 30 degrees. So we get 47.63 pounds. And then our friction force is the kinetic coefficient of friction times the normal force. Try to make that B in there. And 0.25 times 47.63. We get, that looks like 11.91 pounds. What do we do? Sure, getting the same thing. Okay. All right, so we got that out of the way. Now we'll do our kinetics. And we have KE1 plus PE1, the work between 1 and 2, and the KE2 and the PE2. So for our KE1, this thing is moving right along. So we're going to have 1/2 MA VA1 squared plus 1/2, let me go B next, MB VB1 squared plus 1/2, now we also have the rotational kinetic energy right here. So there's quite a bit. 1/2, and the mass of the A is 15 divided by 32.2, turned it into slugs, and velocity is 6.5 feet per second. The mass of B is 55 divided by 32.2, and we found up above that its velocity was 3.467. So if we didn't know to do this ahead of time, we might have to do it over to the side. And then we have I, which is 2.907, and omega 1 is 4.333 squared. And so for my kinetic energy, my initial kinetic energy, I have it over here is 47.40. So let me see what I do. 1532.2 divide 6.5 squared times. All right, so we get 9.841. And then 5532.2 divide 3.467 squared times, and I get, this is like 10.27. Add those last things together, so there's a total of 20.11. And then I'll take 4.333, square it, 2.907 times 2 divide. This is 27, so I get 47.40. Is that what I said before? Yes. 47.40. And these are foot-pounds, or pounds-foot, in terms of work energy, kinetic energy, so it's not the work one. Oops. Just hit the 15-minute mark. That's all I can know is that my screensaver starts to go. So 2, and we have 1 continued. So we are going to now go for our potential energy of 1, state 1. Well, let's see, we have to decide what the datum is going to be. This one is losing potential energy. This one has more potential energy at the beginning and less at the end. So we're going to get his potential energy at state 1, and this is the datum for A. But here's where this thing starts, so this is a good place to start for the datum for B. So the only potential energy we have is for A, and we could either write MAGH1, or we could write the weight of A times H1, which we already have the weight of A. So that's just 15 pounds and 10 feet, so 150 foot-pounds. Remember, that's one of the things that's driving this piece. Yeah, okay, I got that. And now we have the work that's going to be done between these two things. So there's actually 2 parts to the work. There's going to be the force, downward force times H, right? Because we have this force passing through that distance, and they're going in the same direction. So that adds energy to the system. But we also have to take the friction, and I should have wrote a B, friction of B, right there, times our delta S B, 1 to 2. So unfortunately, we already have all those values, so we don't have to put them in. And so P is 110 times 10. We're going to subtract out our friction force, which is 11.91, and the distance SB1 we found to be 5.333. So we're going to get a total of 1,036 foot-pounds according to my Excel spreadsheet, but that's not too hard to do, right? 110, I messed this up, 110 times 10, I could have done that in my head, right? So 1,100, and 11.91 times 5.3333 times, subtract out, sure, we get 1036.5 after we were 0.48, actually. There you go. Okay, and now we want to have the kinetic energy at state 2. We don't know that yet, but we do know that it's going to be 1/2 MAVA2 squared plus 1/2 MBVB2 squared plus 1/2 IC omega C2 squared. So let's go ahead and plug all those in, all the things that we don't know. But let's put them in terms of A, because that's what we want to try to find out anyway, right? So 15 divided by 32.2, VA2 squared plus 1/2. This is 55 divided by 32.2. But now we want VA2 in terms of VB2. Let's see. Well, we didn't actually work it out, but we could, right? So what we would want to do here, we'll write this below it. There's no real room to do this. We want VB in terms of VA. So VA2 is equal to sorry, 1 VB2 and stick it into there is well, we can use omega as the thing to go across, right? So just replace omega C into there, and we will get VB is going to be VA times RI over RO. Right. So up in here, VA2, but then we're going to have 0.8 divided by 1.5. I got the 1.5 correct, right? Yeah, okay. Squared plus 1/2. And now we're going to take the moment of inertia here, 2.907. And now, but we want omega C, but VA over RI, right? So it's VA2 over RI 0.8 squared. RO. Sorry. RO. 1.5. Right? I wrote that underneath there. I guess I'm going to get rid of it. I should have done that on the first page. I just didn't anticipate that I would need it. But I'll just keep going with this. All right. So I got here on my Excel, because I did all of those out right there, that I got this ends up being 2.800 times VA. But let's try it out anyway. 1532.2 times 2 divided. Then I'm going to have I'll just start with this one. 0.8 divided by 1.5 squared times 55 divided by 32.2 divided by 2. And I got something wrong before in the other one. So let me recalculate that, but I'm pretty sure I got all that right. So I get that should be 1532.2 divided and then 2 divided. Right, so I'm going to add those two together. So I have between here I have 0.475. So this might be a significant amount right here. It doesn't seem like it should be. So I have that as 2.8. See, I'm not so sure about this guy right now. Let me try him out. I might have to pause the video here and double check something here. 2.907. Yeah, and then 1.5. And squared, and then times, and then 2 divided. Yeah. I get 1.122, and I want to double check my numbers. This is my means of checking things. So 1 second. PA2 squared. And then the last one is going to be PE2. And remember that is this guy coming up, so it's the weight of B times delta Y B 1 to 2. Right? I think that's all it is. So we have, that's going to be 55 pounds. And we found that delta Y is 2.667. Or 55 and 2.666666 times. So 146.7. 146.7, and these are foot pounds. Let me quick check something. Nope. All right. So we do the whole thing here. Go back to this equation here. Plug them all in. So for the KE1, we have 47.40. For the PE1, we had 150. For the U1 to 2, the work in plus 1,036. 1.122 VA2 squared, and then plus 146.7. So we're going to get a VA2 is equal to, I'll just go 47.4, 150 plus 1036 plus, let's actually subtract that out from there and divide. We can actually divide by that, so divide and square root, and I get 31.12. How come I didn't get that? What? All right, so did I make a mistake somewhere? No, it's not that one. Oh, I see. Huh. What did I do there? Oh, I see. So I think this is correct, but let me double check it here. Because this the other one I converted something into metrics, so that's probably why. if there's any kind of discrepancy. It's probably on that account. And then subtract out 146.7, subtract it out, and divide by 1.122, divide and square root it. Get the same thing again. So I think I got 31.12. And these are feet per second. And I will pause this and see if I can confirm what I made a mistake in this Excel. You know, I like to have certain make things more complicated, so that you'll have to, so you can kind of see, you know, scenarios that you might run across. So what happens next is that this thing has stopped, and no longer is it kinetic energy contributing to what happens to be. This thing is rotating, and this is sliding up together, right? So there's a momentum, or well, kinetic energy is another way to think of it. Kinetic energy that's taking place in the thing, and this thing will stop at the same time as this. I think that's the conclusion that we have to make, that this thing won't stop and then this thing keep on sliding, that they're both going to stop together, that this rope will remain taut. So that's an assumption that I'm going to make. We could do this with an experiment and try to find out whether that's true or not, but for our purposes here. So what we want to do now is set up a whole separate thing and say that we have kinetic energy 2 plus potential energy 2 is, plus the work that takes place equals the kinetic energy of 3 plus the potential energy of 3. Okay, so the kinetic energy of 2 does not equal this right here, right? We could just plug it in. It's going to be minus that. It's actually the kinetic. We could just stick it back into there. That's probably the simplest way to do it. We could also find what the velocity of B2 is going to be. So we could find the velocity of B2 is, we never actually wrote, I erased that other thing that I had. So what I could actually do is, here, I'll cheat. I'll take the, I'll find the omega C2, because I do have that written down, is going to be VA over RO. So that's going to be 31.12 divided by RO, which is 1.5. So you get 20.75, close to it, radians per second. And then I could find VB2, because I have this relationship. So omega C2 times RI, and I get 20.75, and sticking that into there, that's 0.8, right, is RI, yep. And I get 16.60 feet per second. All right, so I need those to be able to do this kinetic energy at state 2. It's just going to be 1/2 mass of B times VB2 squared plus 1/2 I C omega C2 squared. Sure, 55 divided by 32.2. It was almost worth making that into slugs, right, at some point. So we're going to take our 16.60 squared and 1/2 2.907 times 20.75 squared, and square that 55 times 32.2 divided divided. I think that's right. Square that, 2.907 times 2 divided. So I get 860. That seems like a lot. According to this, I get 861. Yeah, so there's some round off thingies going on. I think I trust this other one better. So I'm going to go 861.5. And these are foot-pounds still. And then PE2, that's actually going to be the same thing I had before, right? Right, so we got PE2 is still going to be 146.7 foot-pounds. Did I say that before? Do I still agree that? Boom, boom, boom. It's actually going to be better for us if we reset this. So reset datum and set that equal to 0 right here, right? So this is now the new 0 because we want to treat the thing coming upwards. Now we have U1 to 2. We don't have that external force on it, but we still have the friction. And that's B, the friction force. And that's going to be times the distance it travels up, which is actually the thing we want to try to find out. All right, so that's going to be S delta SB 2 to 3. We're going to add that to SB delta 1 to 2. So negative friction force we found was 11.91 delta SB 2, 3. And now we're going to have the kinetic energy at state 3 is going to be equal to 0 because it's going to pause, right? Everybody stops. And then the potential energy at 3 is going to be that delta SB right here, but it's going to be times the sine of theta. So it's going to be the weight of, see, how did I write this before? Word up there for potential energy at the top. Yeah. Delta Y B 2 to 3, which is going to be, well, the weight of it, 55 times delta S B 2 to 3 times the sine of 30. So what does that come out to be? Just 55 times the sine of 30, or 27.5. Delta SB 2 to 3. And so we plug all these back in, right? So we have kinetic energy is state 2, 861.5 plus the potential energy to 0 minus 11.91 delta S B 2 to 3, and then 0 for the kinetic energy plus 27.5 delta S B 2 to 3. So we're going to find that the delta S B 2 to 3 write it out again, 2, 3. We got 861.5, and all we're going to do is, just add that 27.5 and 11.91, and then divide. And so we're saying, well, we're going up a long ways. Is this true? I think so. Yeah, so it's going up 21.86 feet. Therefore, SB 1 to 3 is going to be 5.333 plus 21.86. And I say that's going to be 27.19 feet. And that's what I got in my Excel. So just using that Excel as a means of checking, because I like modify these problems. I don't have anything to check to see if I got it right. So the velocity of A2, I asked for a velocity, so we need a direction as part of that. We got 31.12 feet per second coming down. And then the delta SB is going to be a total of 27.19 feet. And this was a longer problem than I intended again, but I gave a lot of explanation along the way. It was a 2-page problem. If I had collected enough problems, I could start planning out time by way of pages. And that'd be good. So how long have we go? Ooh, 41 minutes.